You ever try to measure something only to realize that the very act of measuring it changed the thing you were trying to measure? Well, that's not just some philosophical riddle. It's a huge challenge in science and engineering, especially with something you can't even see, like electricity. So how in the world do you measure the invisible without changing what you're looking at? Let's dive in. And hey, don't just take my word for it. The experts at Fluke, the people who make these measurement tools, put it perfectly. The second you hook up a meter to a circuit, you're not just a bystander anymore. You're part of the system, and that has real consequences. So, the name of the game for any engineer or even a hobbyist tinkering in their garage is to make their measurement tool as invisible as possible. The question is, how do you do that? How do you see what a circuit is doing without messing with its natural flow? Okay, let's make this super intuitive. Just picture electricity as water flowing through a pipe. Simple, right? Now, there are two main things you'd want to know. How much water is flowing, that's like electrical current, and how hard it's pushing, that's like voltage. So how would you measure those two things? Well, it turns out you need two totally opposite approaches. To measure the flow, or current, you literally have to put your meter, called an ammeter, right in line with the pipe. But you don't want to clog it up, right? So that meter has to have almost zero resistance. It has to be like it's not even there. But to measure pressure or voltage, you do the opposite. You just tap a voltmeter, onto the side. And to make sure you don't create a leak, that meter needs to have incredibly high resistance, so almost no water escapes. Two different jobs, two totally opposite designs. So you see the pattern here. The goal is always to disturb the circuit as little as humanly possible, to be invisible. But perfect invisibility? That's just not possible. There's always a tiny, unavoidable cost for taking a measurement. So what is that cost? That little price you have to pay actually has a name. It's called the burden. And it's basically the tiny toll your meter takes from the circuit just for showing up. Let's look at a really simple example from Fluke. Imagine you've got a little circuit powered by two brand new AA batteries. That's going to give you about 3 volts to play with. Super straightforward. All right, so you cut the wire, you stick your ammeter in there to see how much current is flowing, you get a number on the screen, it looks definitive, but here's the question. Is that the real amount of current that was flowing a second ago, before you interfered? The short answer is no. And the reason is something called burden voltage. Remember how we said the ammeter needs really low but not zero resistance? Well, that tiny bit of resistance means the meter itself uses up a little bit of voltage. It's effectively stealing a tiny fraction of the power that was supposed to go to the rest of the circuit. And you might think, oh, it's a tiny amount, who cares? Well, in this specific example from Fluke, the meter's burden is enough to throw the reading off by a whopping 6%. That's huge. The current you see on your screen is just fundamentally not the same as the current that was there without your meter. And there you have it, the observer effect in action. You went in trying to be a silent observer, but your very presence changed the outcome. And believe me, a 6% error is definitely a meaningful change, whether you're building a spaceship or just a hobby robot. Okay, so if this is a problem in a simple circuit with a couple of batteries, just imagine the challenge when the stakes are way, way higher. We're talking about scaling this problem up from a small project to some of the most complex systems on the planet. Yeah, at the professional level, things get absolutely wild. Engineers have to worry about so much more than just burden voltage. We're talking about these incredibly tiny, almost phantom currents that come from places you would never, ever expect. Like, you can get a current just from cables rubbing against each other, or from physically squeezing a component. Even leftover chemicals on a circuit board can create tiny little batteries that mess with your reading. So now, think about trying to manage a nation's entire power grid. For the people at the Independent Electricity System Operator, these tiny errors aren't just an academic problem. They can add up to millions of dollars, or worse, they could affect the stability of the whole system. Ignoring them is just not an option. So what's the solution? Well, they have a very official-sounding process called Measurement Error Correction, or MEC. And this isn't guesswork. It's a super rigorous engineering discipline for calculating exactly how off a measurement is, and then applying a specific correction factor to get back to what the real value should be. Whoa, okay, don't worry. You are not going to be quizzed on this formula. The point here is just to show the absolutely incredible level of detail we're talking about. Professionals use math like this to hunt down every last known error. all to make sure the final numbers are as close to perfect as humanly possible. And this is about way more than just making sure a big factory gets the right electricity bill. This precision is what allows them to balance the supply and demand of electricity across the entire country in real time. It's what ensures fairness and keeps the lights on for all of us. So let's bring it all home. Why does mastering this whole observer's dilemma matter so much? Well, because it's pretty much the invisible foundation that our entire modern world is built on. When you break it down, it's pretty cool. At the hobbyist level, the problem is that one noticeable error from your meter's burden voltage, and the solution might be just a quick back-of-the-envelope calculation to get a better estimate. But for the power grid, the problem is this complex web of dozens of tiny errors all interacting, and the solution has to be a formal, legally required system of corrections. But here's the beautiful part. The core idea is exactly the same. Whether you're talking about 2 AA batteries or an entire continental power grid, the path to getting it right is the same. You first have to accept that you can't measure something without changing it, and then you have to be smart about correcting for the change you made. So that leaves us with a pretty fascinating thought. This whole principle of correcting for our own influence is everywhere, hiding inside the tech we use every single day. GPS satellites have to correct for the effects of relativity. Medical scanners have to correct for all sorts of things. Our world is built on these clever fixes. What else around you depends on this kind of invisible precision?